Hi, I'm Bree, and welcome to Concepts for Thinking. Today we're going to be talking about the scientific process and the different forms of inference that are involved in figuring out what's going on in the world. These three different forms are deduction, abduction, and induction. So you're probably familiar with the idea of deduction. If you watch Sherlock Holmes, he likes to say that he's observing phenomena and making deductions about what must have happened in order to create these phenomena. And so deduction is kind of like this word that's used for all different forms of inference, but really it's very specific to a certain kind. It's pure logic. It's moving from, if this is the case, then this other thing must follow logically. The other two forms of induction are kind of moving in the opposite direction. They're saying, given this evidence, what can we infer about the nature of reality? What kind of principles or truths can we infer that can then be used in deductive chains of logic later? But there is a difference between induction and abduction, even though they're closely related. In the Greek, these words have the same spelling except for one letter, whereas deduction is a completely different word. But induction and abduction, I'm going to start with abduction, because this actually happens earlier in the process of scientific investigation. So with science, or like any process where you're trying to figure something out, like if you're a detective trying to solve a crime, it's exactly the same. You begin with observation. And I think that observation is actually given short shrift sometimes. When people think of science, we think of an experiment where you collect data and then you figure out, you reach a conclusion. And that's sort of skipping from a very beginning or kind of a secondary process to the very end. But the very first process is observation, careful observation, attentive observation. And when you observe a phenomenon, then you're able to figure out, okay, maybe this has caused the phenomenon. If you're a detective, you maybe have persons of interest early on. And that move from just observation to a hypothesis is called an abductive inference. You are not figuring out the truth necessarily, you're figuring out some plausible hypothesis. And oftentimes, when people talk about this process, they say that they're coming up with a theory. This is sort of the colloquial way of talking about a hypothesis. But in science, there's a very important distinction between hypothesis and theory. I learned this actually when I was early in my graduate student career. I had an idea for an experiment, and I was talking about it in a laboratory, and one of my good friends now, Katie Renfro, was like, so I was saying, this is my theory of what's going to happen, and she was like, I think you mean hypothesis, and she explained the difference. The difference is that a hypothesis is something that you don't have evidence for yet. It's a guess as to what might be causing something. Okay, so you observe a phenomenon, you make a guess, a best guess, and that's made through an abductive inference about what's plausible. And then you have a hypothesis. Now the next step is not that you test your hypothesis. You have one more step in between. You have to make a prediction. So the prediction is different from the hypothesis, because the hypothesis is a causal explanation, and a prediction is what would happen if you were correct. Right? If your hypothesis were correct, your prediction is you'll set up an experimental design and you'll get a particular finding. And there is therefore a deductive inferential link in between hypothesis and prediction. That is, you're using pure logic to say, if my hypothesis is correct, it necessarily logically follows that this prediction should happen. Now, you're probably not accounting for all variables, and it's not actually true that the prediction might necessarily, in a purely logical sense, follow from the hypothesis, but this is nevertheless a deductive process. You're trying to use logic to move from hypothesis to prediction. So now you have your prediction. And the next step is kind of, potentially the most complicated and difficult step in the whole chain. That's experimental design. And I'm not going to talk too much about that. because this is not for scientists, this is for everyday people. But experimental design is something where you have to figure out how you can control for as many variables as possible so that you're just observing the phenomenon of interest and you're making a very clear prediction, and then you can really rule with a high degree of confidence whether your prediction has been satisfied and you have confidence in the result. So you set up an experiment and you try to control for as much as you can. And now, in a minute, I'm going to give an example for how this can sort of go wrong. But even when it goes wrong, it's not necessarily, all is not lost necessarily. You just have to maybe nuance your understanding of what you've observed. So now you have a hypothesis, a prediction, you've set up an experiment, and all that remains is that you do the experiment and you collect data and you interpret your findings. Now, when you do the experiment, you're interpreting the data. You're now performing an inductive inference because you're taking information that you're getting empirically and you're going, what can I infer about this as far as if it supports my hypothesis or if it disconfirms or falsifies my hypothesis. So are the data close enough to what I predicted that I can say, yes, my hypothesis is confirmed or to some extent supported by these data? Or is it far enough away, are the data far enough away from what I predicted that I can say this really falsifies and disconfirms my hypothesis? So now you've interpreted the data. Let's say that you did a great experiment and the data support your hypothesis. Do you have proof of your hypothesis? No. In fact, process is an iterative process. Science is an iterative process, which means that you have to go through it in different ways, nuance it, critically analyze, have different people perform experiments before you can have a high degree of confidence. And typically what happens through all of that, through different people looking at a problem, through looking at various sources of evidence and bringing it together, is you end up with what's called a theory in science. And a theory isn't just explaining an isolated phenomenon, it's explaining a whole class of phenomena, and it's a little more complicated. So there's a huge distance between a hypothesis and a theory. And even a theory, once it's developed, it's not foolproof, 100% proof of, this is correct. Rather, this is, right now, a pretty good description, but we can always refine and make a theory better. So even though Newton's theory of gravity was pretty good, it's still being refined, and we don't think, physicists don't think they have a perfect theory of gravity yet. But I'm not going to get into that. But I would like to give sort of a related example just to show how the scientific process sort of works and its difficulties and imperfections, and how and its beauty as well. So let's say you are observing the world and you're trying to understand why things fall at different rates. And so because you've noticed that a rock and a feather, they fall at very different rates, a leaf and a rock, a leaf and a feather, various things. And so you use abductive inference to say, well, plausibly, maybe it's that denser things fall faster than less dense things. And so you form that hypothesis and you create a controlled experiment. You take 3 objects that are identical in all their features except for their density. So let's say you get a regular football, American football, a Nerf football, and one of those bronze footballs from like a statue, and you bring them all up to a 3-story building and you drop them all at the exact same time, and you measure how long it takes for them to hit the ground. Well, in this case, you're going to find that the bronze football will probably hit the ground first, followed by the regular football, followed by the Nerf football. And from this, you now have data to interpret, right? You've made an abductive inference that maybe it's density that's key. Now, then you've used deduction to set up your prediction about what will happen in that case. You've tried to create a controlled experiment where variables are all matched except for the variable of interest, density. And then you've performed your experiment and your data, in fact, support your hypothesis. It turns out that the more dense object fell the fastest, and the least dense object fell the least fast. So now you have a finding, and you interpret it, and obviously you're going to say this supports my hypothesis. Now, does this mean you have a theory of gravity and its effect on the rate of objects falling? No. You then need to do further experiments, critical analysis, look at under different conditions, and do the best you can to see to try to falsify what you found. And of course, we've known for a long time that this finding is imperfect. That in fact, the reason you see this difference in the rate of falling is because of the interaction of the density and what it does for momentum and the friction that the objects are encountering. Because if the football is encountering a certain fixed amount of friction, but it has higher density, that means it has more momentum to displace the air on the way down, and so the friction is proportionally doing less to slow it down. So that's why you're seeing this differential. But if you were to take them 3 stories up and create a vacuum where there's no friction, drop all 3 footballs at the same time, they're going to all fall at the exact same speed. So this is something you can maybe infer from looking at the motion of planets, because they're not falling through a medium like air. So to get to a theory of gravity, you have to you take serious your initial finding, but then you look for alternative explanations. You look for ways in which you haven't controlled for every variable, such as wind or friction from the air. And that's how science works. That's how it works if you're trying to solve a crime. It's important also just for thinking in general, because I think sometimes we get really a little bit confused about the difference between a hypothesis and a developed theory, between abductive inference and a fully fleshed out empirical process of discovery. And that can be really problematic. Let's say, for instance, that you are working a case and you have various prejudices. Generally speaking, we all have some prejudices. And so your tendency, as far as what you think is plausible, is influenced by those prejudices. So you are more likely, let's say, to see a person of color as being a likely suspect versus a white person. Well, that's going to shape who you think is a plausible suspect. And it's going to sort of organize your investigation in a certain direction. And if that's all you do, if you're not very careful and scientific, and you don't look at the evidence impartially, then that's really going to influence who you end up finding guilty. So that's just one context in which not going through the process rigorously can be a problem. And it's also just important to realize that a lot of this sort of narrowing down of possibilities that we do is sort of determining how our research goes. And if you're talking about figuring out a theory of gravity, you have hundreds of years. You have as much time as you need, really, to figure out the truth, or something close and approximate to the truth. But when it comes to everyday endeavors, you don't have that. Even if you're working on a murder case, you really don't. You have a certain amount of time, and then you kind of lost your window. So I hope this is helpful. I hope that you start to think about the difference between abduction, induction, and deduction, and how these different inferential processes work together in the scientific process, and then that maybe you apply that knowledge to understanding things in the world. Take care. Oh, and before I go, I wanted to say yesterday was my daughter Billy's first year birthday. I love you, Billy. Happy birthday. All right, take care.